I'm going to do this 2 more times. We got it? All right, welcome back. A couple announcements before we get started. You're almost done. It makes me very sad to say with CS 205A. And so at this point, before your Thanksgiving break, I thought I'd give you a quick check-in to let you know what you have remaining in this class. Your homework 6 was due on Monday, but I suppose you could still be using late days for that. I put out homework 7 on Monday as well, so it is due not this coming Monday, but the Monday after that. And I'm told it actually is easy by the people that have started. But that doesn't mean you shouldn't start early, because that's no excuse. Okay. I may release a homework 8 hopefully by this coming Monday, Thanksgiving. It won't be required, but I'm thinking what we'll do is it'll cover kind of the remainder of the course, and we'll use it maybe to drop your lowest homework grade or play one of these games, because that seems to be something people would like. There are 2 remaining sections. Yeah, is that right? Two sections? Yeah. One this Friday, nothing next week, and then the week after that, presumably you'll have a final exam review. And finally, your exam for this course is on the 12th of November. I've gotten a couple emails from people who have final exam conflicts. You should know that the Stanford University policy is, if you are taking a class, you take the final exam at the time the final is offered. Now, being the nice guy that I am, I'll let you, I will offer one other final exam administration. Otherwise, it becomes a huge headache for me to keep track of papers, make sure everybody's taking it, and all this stuff that really shouldn't matter for me. So here's the deal: is that the last week of class. So when we're talking about PDEs in 205A, even if you have already emailed me asking to take the exam at an alternative time, I want you to email me again, and we will settle upon one time. Okay? And if you take that early exam time, and it will be early and not late, then for one thing, you have to tell me ahead of time. None of this just showing up at the alternative time, and your grade is what it is. Okay? I'm not big on games. Cool. So are there any questions about procedural stuff before we get started today? Yeah, I think it's pretty straightforward, pretty standard. Cool. And the one thing that I'll remind you is that you should go to office hours, because we are a friendly, encouraging, enthusiastic bunch, and we are here to help you. Probably in the last week before the exam, I'll maybe add some extra office hours or something to help you out. And those of you who've been to office hours no doubt know that certainly I and I think the rest of the course staff are perfectly willing to give away homework problems and so on, just in exchange for your delightful company. So there's something in it for all of us. Okay. All right, so today we're going to continue our discussion of ordinary differential equations, in particular this idea of an initial value problem on, again, there's no class next week because of Thanksgiving, but the week after that we'll talk about boundary value problems and partial differential equations. But for now, remember, to give you a little bit of a reminder from last time, the idea is that we're trying to find some function f of t where t is time, yeah, and we're given a relationship between f and all of its derivatives, and also the position, velocity, acceleration, what have you, at time 0. Right? And the idea is that given all of this at time 0, we should be able to march it forward in time. By the way, not necessarily backward in time, depending on the structure of your ODE. Right? And the picture that you should have in your mind is this very famous ordinary differential equation, which I hope we have all heard of, which is F equals ma, Newton's second law, which basically says you total up all the forces that a system has on a particular particle that is equal to the mass of that particle times its acceleration. Right? And this is nothing more than an ordinary differential equation. Right? The forces come from things like your positions and your velocities. For example, if you have wind resistance, that would be a velocity-dependent force. Your mass is what it is. We're not splitting mass over time, at least in this class. And acceleration is just, your second derivative position, right? So this is something you can integrate. Cool. And then, to continue in our review of the last lecture, we defined an explicit ODE, which is one where you can take the highest order derivative and put it onto one side of this equation. And you're kind of hard-pressed to come up with ODEs for which this is not the case. I mean, I suppose you could write them down easily enough, but in real life, they don't show up all that often. But the problem is, if you solve an ODE that is written implicitly in the highest order derivative, then you have to simultaneously solve kind of a root finding problem and time stepping all at the same time, and that's rather difficult, so we don't do that. Yeah. Right, so then if you recall, going in our very quick outline of Monday's lecture, because we're kind of starting in the middle of things today, that we could take any ordinary differential equation, at least that was separable, not separable, the thing that was just in the last frame, explicit. If you could take any explicit equation, and it turns out that you can change it around and introduce variables and substitutions, so that in fact, your explicit equation is nothing more than a first derivative of some vector function equals f of that vector. No time dependence, no higher derivatives, no nothing. Right? And we're going to return to that in a little while in class. Cool? And finally, at the end of class, we defined two different strategies for integration, which both had their own kind of drawbacks and advantages. Right? The first one was forward Euler, which I think is probably the method that you all kind of know and love and would formulate off the top of your head if you had to come up with a way to integrate an ODE, right? Where all you do is you say, okay, I'm going to take my current position, y sub k, and I'm just going to add a little bit of the derivative, and that'll give yk plus 1. And somehow, since the derivative is, my velocity, this makes some sense. Right? And the nice thing about forward Euler, if you recall, is that it is an explicit method for integration. Right? What does explicit mean? It means that if I want to find yk plus 1, it's as easy as just kind of plugging into the right-hand side. I don't need to solve any equations, I don't need to do anything fancy. Now obviously the function f that's defining the derivative could be arbitrarily annoying, but that's sort of a black box relative to the problem we're trying to solve now. And we proved that this has localized quadratic truncation error. That means that if I take a single time step, right? So remember our delta t here is going to be this number h. Yeah, if I step for a single h, then the error that I can make in that single step looks like h squared. And globally, we think of doing approximately 1 over h time steps. And because of that, we have first order global accuracy. Right? And what was the one problem we had with forward Euler is that it's not necessarily stable. Right? So remember, we had this model ordinary differential equation. Right? This is from last time, which is just y prime equals a y. And we already know the solution to this, as I managed to belabor last time, that y of t equals some constant e to the a t, right? I think. And I'm not confident. Yes. And so we know that this equation is stable when a is less than 0. Right? Because when a is less than 0, the solutions to this equation all converge to 0, and that's a nice property, right? Because if I get y of 0 a little bit wrong, as time moves forward, my slightly wrong gets diminished, yeah? But when a is positive, my slightly wrong gets amplified, and somehow this is a very bad unstable property. Right? But what we showed is that even if we assume a is less than 0, explicit Euler doesn't always have this nice converging to 0 property, right? In effect, you can overshoot. Right? And when you overshoot with explicit Euler, right, when this h is too big, then in fact, even though you know that this differential equation over time should just eventually give me that y of t looks more or less like 0, right, the thing that was coming out of explicit Euler was just crazy pants, right? It's exploding. Do you guys see visually why that should be the case, by the way? Right? So we have y prime equals ay, right? And so if we think of there being a slope field here, right, then your slopes, assuming that a is negative, right, kind of look like this, right? The more vertical you get, the more downward pointing they are. And there's no t dependence, right? So this is t and this is y. So they all have kind of the same shape here, right? So what happens if I take too long of a time step? Well, if I start at some point here, then forward Euler just says, look at the tangent that my ODE is giving me and follow it along a straight line for some amount of t, yeah? So the forward Euler instability condition says that, in fact, I followed it so long that by the time I got to my next point here, right, this distance is actually bigger than that one, right? So I overshot like a stupid amount. And so what happens now? Well, this one's going to want to overshoot even more, and so on, right? So and that's why it's exploding. It's actually a pretty straightforward picture. So what did we do? Well, we said, okay, we could just as easily have formulated this backward Euler step, and the only difference between forward and backward Euler is that I'm going to evaluate this f, right, this slope function, at the next time step rather than at my current one, right? So in order to do this, this is called an implicit method, and that's because you have to solve a system of equations. You see, yk plus 1 shows up twice in this formula, right? And do you guys see visually what this thing is doing? Now he's saying, okay, now I'm at this time step here, right? And I have lots of different possibilities for what this y value could be. And I'm going to choose the one for which, if I draw a line from this point to that one, the slope lines up with the slope that's prescribed over here, right? And somehow this makes the system more stable. In fact, we showed last time that backward Euler on our model equation is unconditionally convergent, right? Meaning that it doesn't matter how big an h we choose, it's always going to eventually just go to 0, and that's kind of nice, right? Because if I screw up and I choose a bad time step, or I perturb y a little bit, or what have you, I'm guaranteed that over time my mistakes will get washed out. Now, something we should keep in mind is that this method is still only first order accurate, right? So we can take a huge time step, and what we proved is that if we take a huge time step, things won't explode. But we didn't prove anything about if I take a huge time step, this will be at all physical or look like Newton's second law, right? And these are important to keep separated in our head, right? There's the idea of accuracy, and then there's the idea of stability. And these are two completely separate properties of an ODE integrated. Yeah. So hopefully this story makes sense so far. So if we're going to continue kind of paralleling our lectures from last week on methods for integration and differentiation, right? We started with forward differencing, we moved on to backward differencing, and then the next method we wrote down kind of put stuff in the middle, right? And so for integrals, that gave us the trapezoid method, and for derivatives, this gave us the midpoint formula, yeah? So in fact, we can do basically the same thing here to derive a strategy that is second order accurate globally for integration. So how could we do that? Well, first we open our marker, and if you recall, when we talked about formulas for derivatives, right? You'll remember that the midpoint formula for a derivative was one order higher accuracy than the formula for a derivative that only looks forward or only looks backward. Yeah? In particular, I can write yk plus 1 minus yk divided by h. Well, this thing is equal to what? Well, remember the derivative at y, now I'm going to cheat and say k plus a half, right? The derivative is approximately this difference, centered at k plus a half. Yeah? And then how much error do we have by doing that? Well, the nice thing is that this was quadratic instead of linear, if you remember from before. Okay? So, kind of following the same pattern for how we derived forward and backward Euler, we can play the usual game, multiply both sides by h, so try and find yk plus 1. Yeah? And if we do that, hopefully it's pretty clear what happens. Yk plus 1 equals y. Oh, I'm sorry I have to use notes for these kinds of lectures, but you can see they're kind of technical. Plus hf yk plus 1/2 plus order h squared cubed. Right, so multiply by h. Okay. So this is kind of nice because we have a cube here and we used to have a square there. But unfortunately, we have this f of yk plus 1/2, which is kind of funky because at the same time that we're estimating yk plus 1, we're going to have to estimate this guy as well. But the nice thing that happens is you have an h in front of this f, right? So if he is only second order accurate, then this whole expression is going to be third order accurate because it's multiplied by an h. Yeah? So in particular, if you'll recall the trapezoid rule, right, when we defined trapezoid or midpoint, right, we wrote down the following fact, which was that the average of the endpoints, f of yk plus 1 plus f of yk, right? You kind of expect this to look like yk plus 1/2, and in fact it does. It looks like f of yk plus 1. I have to write smaller. I'm going to be running around the room all day. Plus order h squared. Right? And remember, why do I know that this statement is true? Well, remember that the midpoint rule and the trapezoid rule have the same order of accuracy? Well, this thing looks like midpoint rule. Or that's a lie. This one looks like the midpoint rule, and this one looks like the trapezoid rule, right? He's averaging the two sides, and I just got rid of a factor of h. Yeah? So what can I do? Well, if this is quadratic, right, I can plug in this estimation here, and that quadratic gets multiplied by an h. Right? So in particular, if I note this as star, right? Then star, use the Leon-Simons notation. Then you can also write that this guy is equal to y, oops, there should be a k there, plus h, and now I'm just going to substitute in this expression here, right? So we're going to have h over 2 times the average of the f at the two endpoints. And then what comes out plus order h cubed, which is good. So you see the name of the game here? We were super careful about how we're constructing these types of approximations by looking at sort of our highest order term, right? And then anytime there was something we didn't know, like f of yk plus a half, we can kind of subtract the number of derivatives we need from the h that's sitting next to it, and then find a good approximation. Yeah? So, okay, so great. So remember, in fact, I don't really need the star here. I can just write, this is yk plus 1, right? And this gives us an approximation that we can deal with. In fact, this is an implicit integrator, right? It sort of looks halfway between forward and backward Euler, and because of that, we call it the trapezoid method. Yeah? So the trapezoid method is nice because we showed it has cubic localized truncation error. Remember, the last two methods we had were quadratic, but also, and because of that, globally it has quadratic. Remember, when you go from local to global, you just kind of remove a power of h. Yeah? So great, so okay, so if we're going to continue in our pattern from last lecture, and this is sort of review and also sort of new material, then we have to check a couple things. And the first one is that this integrator is stable. And so in particular, let's plug in and see. So remember, when we check stability, we write down the model equation, right? Y prime equals AY. Remember, Y prime is dy dt. And we're going to assume that A is negative, because otherwise we just don't have hope of stability, because even like the honest to goodness solution here is going to diverge. And our question is, when does our iterative scheme converge to 0, kind of like what we'd expect, right? So if we plug in here, then what do we get? Well, for the model equation, we don't need the vectors anymore. We get yk plus 1 equals yk plus h over 2. And now f of yk is just ayk plus ayk plus 1. Yeah? And now we're going to ignore these higher order terms because this is our integrator. Yeah? So if we group things differently, then we're going to get what? 1 minus ha over 2 yk plus 1 equals 1 plus ha over 2 yk. Did I do that right? Yes. Okay, cool. And so how do I get yk plus 1? I just divide by both sides. Alright. So now, do you guys see what's happening and how this is a little bit bizarre? We have 3 different strategies for integration, and all of them, when you apply to the model equation, are just different powers of some number multiplied by y0. But that choice of numbers depends on your choice of integrators. It's not clear that any one is better or worse than any other. Okay? And in fact here, now, what do we have to do to check that this is stable? Well, we have this magic number here, 1 plus ha over 2 divided by 1 minus ha over 2. We have to check when that thing has absolute value less than 1. Right? So let's see here. So again, it looks like 1 plus, we can write it like this, divided by 1 minus. Hopefully I got the pluses and minuses. Yeah. And this thing is stable exactly when this number is less than 1. By the way, somebody asked about less than versus less than or equal to. Honestly, I don't care. It's kind of clear what's going on. Okay. Well, so it turns out, if you think about it, so remember A, what do we know? A is less than 0, right? And H, we're moving forward in time, is greater than 0. Okay. So in particular, that means this is 1 minus something, and this is 1 plus something, right? So this number is always going to be smaller than this. And in particular, it turns out that this thing is unconditionally stable. I hope. Yes? Right? That is that this ratio here always has absolute value less than 1. It can be negative, but it always has absolute value less than 1. Cool? So that's good, right? So somehow, the question that should be in your head right now is, all right, So why did you bother covering backward Euler? Because this guy is unconditionally stable, just like backward Euler, and he's second order accurate. Backward Euler is first order accurate, right? So like this is a win-win. But naturally, because I'm asking the question, it turns out that this is not the case, right? Because what haven't I told you about yet? Now, there's a mindset in discrete ODE that you should be very careful about. And I know this is applicable to your everyday lives. And when you're walking down the street, you're thinking about different integrators, and we're going to mention several more in today's lecture. It's very easy to think like, well, what really matters here is the order of accuracy. This thing is quadratic and it's stable, and life is good. But the truth of the matter is that usually in our brains we like to think about limits as this number h goes to 0. Yeah? But h isn't 0, right? We're using a computer. We have to choose some finite positive time step. And what's really important is to understand the behavior of this integrator, not just in the limit, but also for a finite positive choice of time step h, right? So it might be that like when h is really small, it happens to approximate the solution very well, but the discrete behavior is like wild and crazy and wiggles about the solution you actually want, for example. It might wiggle really close to the solution you want, but there's still maybe kind of a strange behavior you'd like to avoid. And the trapezoid method is the first example where this is very important. And the reason is, let's consider this ratio here, which I'll call R. And we'll call it R when it doesn't have the absolute value. So actually, maybe I should rewrite this. Yeah, we'll define R of H and A to be the ratio 1 plus 1/2 HA and 1 minus 1/2 HA. Remember, A is less than 0. Okay. Now, before we were talking about what happens when H is small, right? That's what all these integrators and accuracy arguments are about. But now let's take a limit as H goes to infinity, right? Now what happens? Well, H can only go to positive infinity. You can basically ignore the 1 because it's constant, and you're going to get 1/2 times HA divided by minus 1/2 HA. Right? In the end, since the A's have the same sign, this whole number is going to be negative. Right? So if H is sufficiently large, R of H is going to be negative. Why is this weird? I'll tell you why it's weird. And the reason it's weird is that, yeah, this number, so how do we expect solutions of the model equation to behave? They certainly do not oscillate, right? Let's draw it. Yeah, if I solve the model equation, y prime equals ay, then we know we should get e to the at, right? And e to the at is like the world's best behaved ordinary differential equation, right? It goes like this, right? But what did I just tell you? I told you that if h is too big, right? Now the amount of too big does have some dependence on a, but that aside, for any a, when you take a large enough h, right? Effectively, the trapezoid method is going to shoot you down like this, and then up like that, and then down like this, and so on. And yeah, heck yeah, eventually it's going to wiggle into 0, but sort of qualitatively speaking, this is not a good integrator, right? In the sense that it has this weird like oscillatory behavior that you really don't expect for this nice decaying equation. Right? Now you should be asking like, but Justin, obviously this is highly inaccurate. Like why can you draw this picture if we just prove that this thing is third order accurate? And this is sort of goes back to what we were saying when we talked about polynomial interpolation and so on, right? That things that happen in the realm of very itty-bitty time steps are different from when you have very large h's, right? So you're right, that if h is small enough, eventually this number r will be positive, and you will have this nice integrator that moves down this path. But you would better choose a small enough h for that to be the case. Again, remember h is your time step, right? So the smaller time step you choose, the more work you have to do to get to the same time t. Yeah? Now, this leads to an interesting trade-off that I think is hard to analyze, and one that's a little outside of the scope of this class, but is something that for the most part you can either do hundreds and hundreds of pages of theory, or you can just like try 5 different integrators and see which one works for your problem. Now, the trapezoid method is higher accuracy, but it can have really bizarre behavior. Forward Euler is very easy, but it's very unstable, and lower accuracy, and backward Euler is lower accuracy, but very stable. right? So you sort of have three different pictures you should keep in your mind. And the trapezoid rule is an interesting case, right? Because what is the advantage of stability? The advantage of stability, I'll tell you, the advantage of stability is that you can take a large time step, right? But then this other weird qualitative behavior starts coming out of the woodwork exactly when that happens. So yeah, the solver is stable, it's not going to like wing off to infinity, but it's still not an accurate or interesting solution, right? So sort of the extra stability that you get out of trapezoid is sort of limited usefulness. Okay. Right. Again, stability, accuracy, two completely separate questions. No, not completely, but like 98% complete. Okay. Oops, I got ahead of myself. Okay. So again, from a high level, what is the pattern that we've seen so far? We've seen that convergence of an integration scheme as h goes to 0 isn't the whole story. And then we said, oh great, and that was our story as of the middle of last lecture. Then we added something last lecture, which was that, yeah, it's not the story, we need to consider stability. In fact, now we know that that's not the whole story. You also have to consider behavior for fixed h is greater than 0. Yeah? That in practice, we don't take limits as things go to 0. We do choose some finite positive time step, and we should know what our integrator does for that finite positive thing. In fact, this mindset is a relatively recent one in research, even. Right? People kind of have gone back to this theme and reanalyzed a lot of the integration schemes that we'll talk about here. For example, one of the very interesting classes of things that is nowhere near the kind of work we'll be able to do in this class is to say, okay, maybe I'm doing a physical simulation, right? I'm like, I tossed a bunch of balls into a can and I'm watching them bounce around, right? Now, what happens if I solve this with backward Euler? Right, let's say I have ideal bouncy balls and they're just going to keep bouncing, you know, until infinity, conserving energy, right? Now, if I run with forward Euler, as I move forward in time, my ball is going to start bouncing higher and higher and higher, right? Because forward Euler tends to overshoot. If I simulate with backward Euler, I'm going to be damping out this system, right? So slowly my balls are just kind of stop, right? But there's a class of integrators that are called symplectic integrators, which are super cool. Because what they say is, what I really care about is that energy is conserved over time. Right? That maybe my simulation is a little bit inaccurate, but what I don't want to have happen is globally that my balls start to go really crazy or dampen out. Right? So a symplectic integrator says that the average over time, for example, the kinetic energy of my system should be the same. That is, I shouldn't globally dampen something out. And it turns out that you can very carefully construct integration strategies basically by writing down the formula for energy and then using that to make an integrator. The same way that we wrote down, you know, divided differences and used those, that actually conserve energy. And this is great, especially for computer graphics applications, where what you really care about is that your video game doesn't explode and doesn't get boring. And maybe you don't care so much about accuracy, because, you know, as long as it's kind of physically plausible, that's okay. Right? So there are lots of different contexts, and you should basically choose your integrator very carefully. You should Google this, right? You can take first order Euler, and you can turn him into symplectic Euler, and it has some of these properties. It's not too hard. Right. So again, from a high level standpoint, right, for the sort of like midtermable, final example material, what you should know is that you really need to understand both qualitative and quantitative behavior of your integrator, because neither one in a vacuum is enough to make an educated decision about what you want. Okay, enough of this high level stuff. Okay, so we can continue to make more and more different types of ODE integration schemes with all kinds of cool properties and drawbacks and things, and we're only going to spend about a half a lecture on this today because at some point it just becomes obscure, but it is worth acknowledging at least the sort of main classes of integrators that you're likely to see in the wild. So there is one class of integrators that is particularly important, and unfortunately the two names that are attached to these integrators I can never say properly. Rungkutta, I believe, is correct. I always thought they were from India, but apparently they're actually from Germany. I learned last night. Anyway, that aside, we're gonna derive those, and they're based on methods for quadrature, right? So, like, so far my arguments have mostly been about discrete derivatives. Now we're gonna use quadrature, and how do we do that? Well, we're gonna use the fundamental theorem calculus, right? Because we know that y at time k plus 1 is equal to y time k, right? Plus the integral from tk to tdk plus 1 of what? Well, y prime of t, yeah? This is just the fundamental theorem of calculus. But we know, right? We know that y prime is nothing more than f of y of t. Now, why is this formula like sort of, tautology isn't quite the right word, but it's not 100% clear that this formula really tells us anything about life. Because while it is true that y satisfies this expression, we don't know y of t, so it's like a little bit worthless. We can't actually take this integral, right? But one thing we could do is try to approximate this integral, right, and use the coefficients that come out of quadrature to derive a method for integration, and that makes these integration schemes whose name I won't try to pronounce. Yeah? All right. So let's try and do this. All right. So the method, and I actually googled the name of this one. It's Hoyne's method. Apparently rhymes with coin. And this method is sort of the first version of one of these integrators. So here's what we're going to do. Okay. Yes? Okay. Sorry, this lecture makes me nervous because there's like a lot of math. Math is hard. Alright. So, right. So let's say that we go back to our formula we have here. Oops, not that one. What is that? Ah, okay. Let's say we go back to this observation we've made here. And we say, okay, well, this formula is kind of tough, but we can substitute it in the trapezoid method for integration. And in fact, this is just going to recover the trapezoid method for doing ODEs that we derived like 10, 15 minutes ago. Right? Because if I write yk plus 1, that's a plus. I don't know what's going on here. Right? Use yk. And now we're going to approximate this integral with right, f of yk plus 1. Or, yeah, plus f of yk. Sorry. Yeah, so just averaging these two guys. Okay. And this is plus cubic air. Right. And notice, what did I do to get this expression here? This is nothing more than the trapezoid rule. Right? Now, the trapezoid integrator, we already decided, it has a lot of bad properties, right? He wiggles around and he's implicit, right? So not only do we have to do a linear solve, but what comes out of that linear solve isn't even that useful. Yeah. But one thing, and the additional observation that Ron Kutta made was that not only can you use a quadrature scheme to get some expression that looks like an implicit integrator, but you can also approximate yk plus 1. Right? What is yk plus 1? Well, he's exactly what you're trying to find. But what if I use a worse integrator for this yk plus 1 than this one? Well, look what happens. I have an h in front of this f. Right? So if I get this term a little bit wrong, I'm going to diminish the amount of error by multiplying by another small number. Right? So in particular, what they did is they said, okay, well, f of yk plus 1 is approximately equal to f of yk plus hf of yk. What did I do here? Well, I applied forward Euler integration to get some approximation of yk plus 1, and I put him inside of f. Right? This is really tricky. Because look what happens. Well, okay, so we know then that this is plus order h, for example. Right? But now that order h gets multiplied by another h on the outside. Right? So this whole method is no longer cubic, but at least it's quadratic. That's great. It's still a convergent scheme for integration, and unlike the trapezoid method, this one